Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the first day of week 10. In ninth week, you have seen how to derive weak formulation for two-dimensional elasticity problem. And this week, we will be mostly talking about the implementation part. We'll take some example, solve it, and also write a finite element program for two-dimensional elasticity problem, and then use some other problems to see the convergence, error, and so on. So, but before that, so this week what we'll do is this. But before that, there are few things which we did not discuss in the previous weeks. We intend to have those discussion in this week as well. First is we have seen how to write program for two-dimensional scalar field problem. We have taken example of heat conduction problem. There are many other problems that can be expressed through the Poisson's equation, and heat conduction is one of them. And that week we told that there is another problem we'll be taking, that is torsion problem. That week we couldn't do that. So we will start this week by revisiting the two-dimensional scalar field problem and take torsion example and apply finite element method to get the solution. And then we also had a discussion on how to construct shape functions for quadrilateral elements, higher order quadrilateral elements. We discussed Lagrange element, then serendipity elements. But then as far as the discussion on triangular element is concerned, so far we know how to write shape function for three-noded triangle, means constant strain triangle. In this week, we will also see how to write shape functions for higher order triangular elements. We will also see what is the natural coordinates for triangular elements. And then finally, once we have that, finally we will take some examples of two-dimensional elasticity problem, write a code, and then solve some example. So today let us start with the first one. Okay, so this is the same slide which I had shown you in that week when we discussed two-dimensional scalar field problem, Poisson's equation. There are many physical processes can be represented to Poisson's equations. We had a detailed discussion on heat conduction problem, and today we will take this torsion problem. So torsion problem equation, the main equation remains same, but the variables will be different depending on the problem we take. So in this case, the source term becomes 2, and then K becomes 1, and the material constant is essentially the shear modulus. And then this is how the flux term related to the stresses like this. But before we take this equation for granted and just straight away apply finite element method, let us spend some time on revisiting the derivation of this equation. We'll discuss very briefly the derivation, what you have already done in theory of elasticity course. So if you any theories always start with an assumption, or assumptions rather, because that is the most important part, if not one of the important parts of any theory, because assumptions are essentially the limitations. Therefore, it is very important when we start any theory to understand the assumptions. So, assumptions of circular shaft under torsion, we know this is each cross section rotates as a rigid body about the longitudinal axis. Rotation is linear function of axial coordinate, and then a section which is plane. This is true for when your deformation is small, and plane section which is perpendicular to the longitudinal axis remain plane. But if your shaft is not circular, any arbitrary cross section, some of the assumptions are not, we need to change some of the assumptions. Like first one will become the projection of each section, the xy plane rotates as a rigid body, and the rotation of the projected section is linear function of the axial coordinate, and plane section may not remain plane, which was significantly different from the assumptions we had in case of circular cross section. Okay, so we know this. So let us take a bar, which is the cross section is defined by xy plane, and then the longitudinal axis is a z axis. We take a cross section, and then this cross section is this. So this is x, y, and this is omega is the boundary of this cross section. When we apply finite element method, we will see we will take this as the domain, and then this is the boundary of the domain where the essential conditions and the natural condition need to be specified. Okay. Now, first let us understand what is the governing equation, then we will see what are the boundary conditions we need to apply. Now, suppose this is a section and take any point P on the section at an angle theta, and suppose this is distance OP at a distance R. Now, when we apply some torque like this, then the angle, this point P will move to another point, say this is P dash. So, this point will move to this point P dash. And suppose this is R and this angle of twist is beta. Now, from this geometry, we can say that P dash is equal to R into beta, provided beta is very small, and that is the assumption. Our assumption is valid for small deformation. So, this is fine with for small deformation. So, the component U will get RB sin theta, which is essentially B sin R sin theta gives you y, so minus beta y, and then similarly we can have v. So, this is the component in x and y direction. Now, since here in this case your there will be out of plane deformation as well in the z direction as well, then before we do that, I would like to take you to this assumption, which tells you that rotation of the section is a linear function of the axial coordinate. Means if the rotation is theta, suppose theta is the angle of twist per unit length, if the angle of twist is theta, then this rotation, this beta will be the linear function of z. So, this theta is the angle of twist per unit length, and z is the direction, z is the along the longitudinal axis, what is the length. Okay. Length means the point, the section we are talking, what is the position of the section in the z axis. Okay. So, now, so this gives us u is equal to this, v is equal to this, and suppose w is equal to this. Now, theta is the angle of twist, we said per unit length, and phi is, we don't know, we have to determine phi. Phi is called warping function. We will see how to determine phi. Now, so this is the description of u, v and w, and then we know this is the definition of strains we have learnt in linear elasticity, and but in this all these component of strain, all components will not be non-zero. For instance, this will be 0 and this will be 0, all this normal component will be 0, and then this will also be 0. Only non-zero component we have is this and this. Okay. So, only non-zero component we have epsilon yz and epsilon zx, and once epsilon yz and epsilon zx, if we substitute this value of u v w, we'll get this. Okay. Now, next is we know this is the strain, and then we know what is the relation between strain and stress. These stress components will also be 0. And we know the relation between stress and strain, the constitutive law, the Hooke's law, we know generalized Hooke's law. This gives you the stress components, and this by G is the shear modulus. Okay. So, now we know the stress component. So, once we know the stress component, now we know we have seen in the last week, this is the equation, equilibrium equation in a two-dimensional elasticity problem. And in 3 dimension, this equation looks like this, and then if we substitute these in this equation, all the component of stresses, we eventually get equation like this. Only one equation we will get. Now, with this, now we know what is for sigma and sigma in terms of phi. If we substitute this, we will get this. Okay. Now let us define another function psi, which is called stress function, like this, related to phi as this. Okay. Now if we substitute psi in this equation, this is the equation we know, and if we substitute phi in this equation, we will get an equation like this. And if you recall, this is the equation we have seen that this is the Poisson's equation, isn't it? So in this, that f is equal to -2, this is how the -2 terms come, and k is equal to 1, and t is equal to t is psi here, which is the field variable, the primary variable we need to determine. Okay. Now this is the equation defined on, this is the governing equation on the entire domain. Now along with that, we need to have some boundary conditions, essential boundary conditions and natural boundary conditions. Now let us see what is the natural boundary. Essential boundary condition, anyway, once we have the finite element formulation equation, global equation, then we can impose the essential boundary conditions. Let's see what is the natural boundary conditions. Here you see the traction, if you take at any point on gamma, traction is defined like this, and the traction will be 0. And now if we substitute sigma and sigma in terms of psi, we know that this is the expression of sigma and this is the psi is related to phi, and if we substitute that, what we get is this, and this will give us psi is equal to constant on gamma. But now constant could be any value. Now you see, our ultimate role is to determine the stresses, and then finally stress, strain, and then finally displacement, right? Now stress required a derivative of psi with respect to x. Okay, so whatever may be the value of constant, that constant, it will not contribute anything to the stress field, because we have to take the derivative of that constant, which is anyway 0. And if that is so we can straight away write the boundary value problem for torsion as this. This is the governing equation on omega, in omega, and this is psi is equal to 0. If you put, whether you put it 0 or any other constant, your stress is going to be same. So this is the natural boundary conditions we have. This will automatically come in the weak form, and then we have to impose the boundary conditions, essential boundary condition, once we have the global equation, right? Now with this background, we will not go into the finite element formulation, weak formulation, because we have already seen what is the weak formulation for Poisson's equation. We will straight away take an example and then try to get the solution using finite element method. Now take this example. This is a squared domain, 0.5 by 0.5. I have not given the unit explicitly in this figure. So the essential boundary conditions are this: psi is equal to 0 here and psi is equal to 0 here, and the natural boundary condition, the flux, boundary flux term is defined as this. Here it is 0, here it is 0. Here our life is easier in the sense that boundary flux term is 0, so we really do not have to we do not have to do that boundary integral to get the flux term. So this is 0 in this case, right? So straight away that part we can put 0. Okay, so now one additional thing we will do today is first let me take you to the program, to the code. Okay, now this is the code we have already seen in the in week 8, right? This is a code for a quadrilateral, for solving Poisson's equation using quadrilateral element, 4 noded quadrilateral element. So we will not go through the code details again, but one more thing we will do here is we will also see the code with another element, 8 noded quadrilateral element. Okay, entire thing will be same, only difference is now you have 8 nodes. So for every node, every element we have 8 degrees of freedom, and then for every element we have 8 shape functions. Okay, but the other structure of the code is exactly same. Now what we will do is we will see 2 kinds of convergence. One is, so for quadrilateral element, for this kind of quadrilateral element, we know that our safe function, our approximation is bilinear. Then this approximation becomes quadratic. If we have this for 8 noded element, we have seen, then we have approximation, better approximation. So we will see that first we will do with increasing the number of elements, what happens to the solution, and also we will see by changing the elements, 4 noded quadrilateral and then 8 noded quadrilateral for same number, same kind of discretization, what results gives you better convergence and faster convergence. Okay. So let us first start with 4 noded quadrilateral. So this is the domain already written here. So H is equal to 2 means as we had seen in the last in week 8, H is equal to 2 means we have H is equal to 2 means the entire domain is divided by one element, it is discretized by one element. In a parametric domain, our size of the element is 2 by 2, that's why it is H is equal to 2 here. Okay. So these are the Gauss points and their integration weights. So this is our k term is 0 in this case, k term is 1 constant term, and boundary this f source term is 2, and then boundary flux term is 0, psi is equal to del psi del n is equal to 0, we have seen. So this is the discretization we had already seen. So this is the boundary conditions we have on this boundary, and on this, these are the essential boundary, and this is natural boundary conditions. So this is how the boundary boundaries are identified for both the cases. Then rest of the thing is same. Okay. Now, so let us first get the solution with one element. So what we will do is, as I said in one of the weeks, when we talk about convergence, here it is not the value at a particular point, we have to see how the solution as a whole converges to the true solution. When we talk about error, it is not an error at a particular point, it is error in the solution as a whole. But just for the checking, we will take one point, say we will take this point. We will take this point to check the convergence, and we can take this point as well. So this point will be your x is equal to 0, 0, and this point is x is equal to 0.5 and 0.5. These 2 points will check this point is, there is no point because psi will be anyway 0. So let us concentrate on this point and check what happens to the solution or the value of psi at this point. Okay. Now, so first is we need to write the solution also, because eventually we have to check the convergence. So get the okay. So run it. This is our discretization. We have just only one element, and then this is the contour plot of in this case psi. So let us see the value of psi. So value of psi will be u1, because this is the first point. This point is at 0, 0 is the node number 1. So let us see u1. u1 gives us 0.1875000. So let us so let us write this. So it is 1 by 1, 1 by 1. Our solution is solution is 0.1875. So right, this is 0.1875. Next we will take 2 cross 2, means 2 element in x direction, 2 element in y direction. Okay. Now let's do that. So if for 2 element we have to make it 1 and then run once again, and this is the contour plot, and this is how this your discretization look like. you can close it. Yeah, this is how our discretization looks like. Where is that? Yeah, this is the 2 by 2 and our U is 0.15536, 0.15536. So this gives you 0.15536. Now we'll take 4 by 4. 4 by 4 means we have to take, this is 0.5, 0.5. So this is the discretization, and U will be 0.149, 0.1492. 0.1492. Now we take 8 by 8. Make it 0.25. Usually when we talk about convergence, now we have two different level of discretization, right? So your lower level of discretization should be the subset of the upper level of discretization. The reason is, I could have taken, instead of 8 by 8, I could have taken 9 by 9 or 10 by 10. The reason 10 by 10 is not taken, because when you take 10 by 10, the nodes which you had already taken in the previous level discretization, those nodes are no longer as a part of the discretization now. So if you take 2 by 2, then again 4 by 4, and then again refine it, then 8 by 8, then further 16 by 16. So whatever points we have, nodes we have in case of 8 by 8 discretization, that many points, the location of those points will remain same in 16 by 16 discretization, plus we have some additional points. Okay, so that is how we usually check the convergence. So it is 0.1478. So this gives you 0.1478. Let us do it by 16 by 16 as well, and this will take 125. Okay, so this is the discretization and this is the contour plot, and let's see this. This is 0.11475. Okay, so this is 0.1475. We can further check with 32 by 32 discretization, but we have seen it is fairly, it is now convert. So this is for Q4, right? Now we will use Q8. Q8 means, so this is our element was like this, 4 noded quadrilateral. Now Q8 we have element, you recall we have discussed serendipity elements, this is same elements. Okay, so we will see what happens to this with this. So let's go to the code. The code will remain same, but only thing will be here. Now our only thing will be here, we have total 8 nodes. So per node we have 8 degrees of freedom, and therefore total 8 nodes, and other things are same. This is element level numbering, this is global numbering, and then this is our this is the essential boundary, this is the natural boundary, initialization, and this is initialization of the coefficient matrices and the vector. 8 by 8 now coefficient matrix. These are the mapping between global numbering and the local numbering, and finally these are the shape functions. 8 shape functions. They are derivatives with respect to z, the xi direction, derivative with respect to eta, and this is how your Jacobian is defined. And B will be inverse of Jacobian into del phi term. So this gives you the inverse of Jacobian, and K will be your using Gauss point integration technique, that I and J are the position of the E and Z are the position of the Gauss points, and Wi, Wg are the weights associated with the Gauss points, and this will give you the source term, and this is the assembling of the coefficient matrix. Now we have 8 by 8 matrix, that's why it is written like this. Okay. Now, so this is source term will be 0 anyway, a source term, not the boundary integral term anyway, will be 0 because the psi is equal to 0, del psi del is equal to 0, and rest of the thing is same. You identify based on the known and unknown information and then get the condensed matrices and then solve it. So, first let us get the solution with with 1 by 1 discretization, means h is equal to 2. So, this is the solution. Then okay. Okay, let us first close all the figure. Yeah. So, our discretization is this, and our discretization is this. There are only one element, and let us check what is u. U will be 0.132, 0.132 say 4, 0.1324. This is 0.1324. Now, let us take with 2 by 2 mesh. So, take h is equal to 1. Yeah, this is how the discretization look like, and then u will be 0.147, 0.1471, 0.1471. 0.1471. Okay, and then next let us take 0.5, means 2 by 2. Okay, so this gives you 0.1473, 0.1473, and then you can further discretize it, make it say 0.25, 0.1473, 0.1473. So, 0.1473. So, this is same. So, let us do it, which is not necessary, but just out of curiosity, let's see what happens at 1 to 5. So, this is our discretization. You can see this is the contour plot, and let us see the result, 0.1473. So, this is again 0.1473. So, 0.1473. You check whatever result we have obtained. So, this is now converged result. So, even if we further increase it, now there are two things to be. Now, with this note, we can get the convergence if we take up to 3 decimal places. So, with 8 by 8 discretization for Q4, we get the convergence. Okay, and for Q8 the same convergence we get with 4 by 4 disc. Even with 2 by 2 discretization, with Q8 gives us almost converged result. If we take only 3 decimal places, then with 2 by 2 discretization we get the converged result. But the similar kind of result to get, we needed at least 8 by 8 or 16 by 16 discretization for Q4 element. So, the values that you can see on your screen, these values tells you two kinds of convergence. One is H convergence. H convergence means the convergence we obtained by increasing the number of elements. So, if you go in this direction, this will give you H convergence, right? Now, if you go in this direction, this will give you P convergence. Okay. So, another convergence is by increasing the order of element, we can get the solution. Okay. So, this is the torsion problem. The philosophy is equations are same, but now we have already seen solution of this equation. Now, we have seen today how the solution can be improved by increasing the order of approximation. Okay. Now, with this we will stop today now. Now, next class we will start triangular elements. We will see higher order shape functions for higher order triangular elements, and those triangular elements we will be using to see some of the elasticity, to find the solution of some of the elasticity problem along with Q4 and Q8. Okay. So, see you in the next class. Thank you.